INSEE is a proud member of the Siam City Cement Group Public Limited, a leading cement manufacturer in Southeast Asia. The Siam City Cement Group provides world-class construction materials to a host of countries around the world. This includes Cambodia, Bangladesh, Vietnam, Thailand, Indonesia and Sri Lanka. With a plethora of landmarks and buildings that define the skylines of these countries, the Siam Cement Group pledges to be a role model in corporate governance and sustainable development. INSEE Cement, Sri Lanka's premier cement manufacturer, is the brand behind our country's leading cement products and the driving force behind making Sri Lanka more sustainable. With a reputation built on outstanding performance in the quality of our products, unparalleled customer service, the dedication of our employees, our respect for the communities in which we operate, and our ambition to set the standards for the industry of tomorrow, we have contributed to the growth of Sri Lanka with iconic developments across the island. Just to name a few: the Lotus Tower, Altair Residencies, the Colombo South Harbour, Southern Expressway, Mattala Airport, the Kalladi Bridge, the Kotalavala Defence University, Mahinda Rajapaksha International Cricket Stadium. INSEE has cemented its position as the most preferred local manufacturer of cement in Sri Lanka, with its widespread distribution network comprised of over 7,000 dealers in retail segment located island-wide. Today, we have 2 plants in Puttalam and Galle and 2 terminals in Galle and Colombo. INSEE's Sunstar brand is Sri Lanka's first cement product to be awarded the Green Labelling certification by the Green Building Council and was the first blended cement to launch in Sri Lanka. INSEE has a wide portfolio of cements and services to suit all your construction needs. The most popular among them, INSEE Sunstar, INSEE Mahavali Marine Plus, INSEE Extra for mass pouring concrete, INSEE Rapid Flow Plus, INSEE EcoCycle, INSEE Concrete, Conwood by INSEE, state-of-the-art innovation and development facility. Having been a part of Sri Lanka for almost a decade, we will continue to build on our long heritage of shared loyalty, creating trusting relationships with our business partners, people and community, and delivering our promise of building the nation.
Professor Mudalige Tishan RENUKE JAYASINGHE, BSc Engineering Honours Moratuwa, PhD Cambridge, Chartered Engineer MIE Sri Lanka, MSc Sri Lanka, holder of Toll Building License of Urban Development Authority, and Senior Professor at the Department of Civil Engineering, University of Moratuwa. Sir, we are on behalf of the INSEE management, the management of Siam City Cement Lanka Limited, we would like to welcome you to this session. Before we proceed with the next items, may I give a brief introduction about the theme today, the optimized and sustainable super tall buildings. In order to reach optimized structural design of tall buildings, it is ideal to have structural engineering consultants involved from conceptualizing and architectural design for input based on naval configurations. Structural optimization includes immaculate planning that reduces wind effects, use of PT for slabs and other elements in order to minimize reinforcement usage, risk assessment for key elements, use of high performance concrete as allowed in modern Eurocodes, etc. Further, it is important to undertake the optimization of foundations. This could be done by using high performance concrete coupled with very high level of skin friction when anchored in bedrock, as often found in Sri Lanka, and the use of single large diameter piles, etc. It is also essential to use alternative and waste-based building materials to improve the sustainability of the building and achieve a drastic 40 to 50% reduction in the overall average construction budget today. All these different aspects will be discussed in detail with examples from recently constructed tall buildings like Altair and future super tall buildings of 150 to 250 stories without any setbacks, where the floor-to-floor height can be varied from between 3.2 meters to 4 meters. So today's session is on, ladies and gentlemen, on optimized and sustainable super tall buildings. Before we proceed with the lecture, may I invite our captain of our vessel, behind the person who is behind all these concepts. To give away the welcome speech, may I invite Mr. Jan Koenig, Executive Vice President, Director, Marketing, Sales and Innovation of INSI Cement. Jan, over to you to welcome the gathering.
Good evening, everyone. Can you hear me?
Yes, you're audible, Jan.
Okay, thank you. Can you see me? Can you see me, Ishan?
Not yet, Jan. Not yet, but your voice is very clear. Okay,
Yeah,
now we can see you. Now we can see you.
Very warm welcome to everyone. Good evening to Sri Lanka. I'm right now in Germany. But very warm welcome to all of you for today's session on optimized and sustainable super tall buildings. More and more in the world, we are getting into vertical structures, into high-rise structures as urbanization progresses. And for sure, with urbanization, many challenges come along, whether it is CO2 reductions, overall emissions, carbon capturing, but by building tall structures, for sure, it's very, very important to look at how can we build them as sustainable as possible. With its sustainable materials, foundation optimization, can we include waste from previous demolitions, etc., high performance concretes, so that overall we optimize our resource input and make it livable for everyone, the society around it as well. Shadows are created. All of those things need to be looked at the design stage already, so much earlier, before we actually see the very first stone or concrete truck moving to such a construction site. And I'm very happy that we have Professor Mudalige Tishan RENUKE JAYASINGHE today with us as a follow-up from last month. So thank you very, very much, Professor, for joining today. And we are really looking forward to your excellent presentation. And with that, I'm handing over right again to Tishan, and let us have a fantastic session. I'm very much looking forward to it. And please, anyone again, you can use the chat function or the Q&A function. And at the end of the meeting, we'll address all of your questions. Thank you very much, Tishan.
Thank you very much, Jan. Jan Koenig is our Executive Vice President, Director Marketing, Sales and Innovation. Thanks again, not only for the words, but also for the leadership to conduct this kind of sessions under INSI Eye to Eye, Innovation to Industry. Ladies and gentlemen, I am privileged to present the resource personality today to conduct the session on optimized and sustainable super tall buildings. Today's resource person is Mudalige Tishan RENUKE JAYASINGHE, BSc Engineering, PhD Cambridge, Chartered Engineer MIE Sri Lanka, MSSC Sri Lanka. Professor Tishan RENUKE JAYASINGHE completed his BSc Honours First Class in Civil Engineering in 1987 by University of Moratuwa, Sri Lanka, and research leading to PhD titled Rationalization of Press Concrete Spine Beam Design Philosophy for an Expert System at the University of Cambridge, England. Followed 1.5-month advanced course on Building, Energy and Environment in Lund University, Sweden. In terms of career summary, February 1987 to September 1888, he started his career as an assistant lecturer, Department of Civil Engineering, University of Moratuwa, Sri Lanka, and then research scholar, lecturer, senior lecturer, associate professor, senior research associate, and from February 2003 to February 2011, professor, Department of Civil Engineering, University of Moratuwa, and then from February 2011 to date, senior professor, Department of Civil Engineering, University of Moratuwa. In terms of foreign collaborations, August 2019, visiting academic Department of Architecture and Civil Engineering, University of Bath, United Kingdom. March 2019, visiting academic Department of Civil Engineering, University of Liverpool, United Kingdom, and visiting academic in 2018, Department of Architecture and Civil Engineering, University of Bath. Visiting Academic, Department of Civil Engineering, Queensland in 2018, University of Technology, Australia. In June 2017 to August 2017, visiting Academic, Department of Architecture and Civil Engineering, University of Bath, United Kingdom. Special award, in terms of special awards, Professor Tishan Jayasinghe has acquired the Presidential Award for Scientific Research for 2017 publications, awarded by National Research Council Sri Lanka, given to the top 100 scientific publications. Award for the Research Excellence for the publications in 2018 by University of Moratuwa. ISL Award in 2011, Best Article by Corporate Member in the journal Engineer. Chartered Engineer Award, Engineering Excellence Awards 2011 by Institute of Engineers Sri Lanka. Cambridge Commonwealth Trust Scholarship to read the PhD in 1988. UNESCO Team Gold Medal for Best Engineering Graduate 1985 to 86, University of Moratuwa. Some major consultancy assignments, Chairman of 3-member Presidential Commission appointed to investigate the collapse of metal underpass and review suitability of underpasses over 35 kilometers stretch of Southern Highway under construction in 2009. Leader of the design team that proposed this and the strengthening of metal underpasses with concrete lining in Southern Highway for over 40 structures in 2010. Check engineer for 35-story Sky Garden apartment building at Rajagiriya by Marga Engineering. Check engineer for 46-story Clear Point apartment building Rajagiriya for Marga Engineering. Guidelines for selection of structurally efficient and economic structural forms for domestic building for Selinco Homes International Private Limited. Structural assessment for the dynamic behavior of Daduroya Steel Truss Bridge to assess the safety against the stress developed due to dynamic response in 2011. Assisted MAS Holdings to plan, design and construct a green factory for 800 employees with the use of many principles of sustainable development as applicable to built environments in 2007. This building complex was awarded LEED Platinum rating. There are many more to go. I am privileged and honored to introduce Professor Mudalige Tishan RENUKE JAYASINGHE to the audience. Sir, may I invite you very warmly and honorably to conduct the session on optimized and sustainable super tall buildings. Sir, over to you.
Okay. Optimized and sustainable tall buildings. And thank you very much for that kind introduction. So first I'll give you an overview of the presentation. Introduction to Sri Lanka, tall buildings in Sri Lanka, for examples, water load, vertical load bearing load resisting system, the lateral load resisting system, mathematical models, and code of practice, fundamentals and applications, future of super tall buildings with examples, special facades to control wind forces, use of waste-based partition materials for apartments, role of Euro codes for super tall buildings, and conclusions and acknowledgement. Okay, first look at where we are. Small island, 64,000 square kilometers, and population of 22 million, about 2.5 million lives in other countries. So because of that, we have significant foreign exchange inflow to the country. And because of that reason, we have considered that it's a good country to have tall buildings, and especially in Colombo and many main cities, it's possible to consider tall buildings, especially the apartment buildings, so that we can have a large number of people living in very close to the railway stations and so on. And we are having tropical climatic conditions. Tropical climatic conditions are considered very good for retirement by many people. And because of that, we can see if we have right policies, it's possible to have many Sri Lankans who are migrated to other countries, coming back to our country to live here during their retirement, and that can generate significant demand for tall apartment buildings. So if you look at some of the statistics, in Sri Lanka, we have in tropical climatic conditions, and because of that, we have a very low carbon footprint, and our carbon footprint is less than 1 ton. And again, we have government policy geared for increasing the forest cover, and also there's a shortage of natural resource-based building materials, and because of that reason, we are keen to go for alternative materials like EPS-based lightweight wall panels, where 80 to 90% of the EPS is already used once, and then again we use fly ash. Then we have autoclave blocks manufactured in Sri Lanka, and then again we can have EPS-based lightweight blocks manufactured in Sri Lanka. So converting waste to building materials is a good business in this country because we have high prices for natural resource-based building materials. So if you look at buildings, this is the tallest building at the moment in Sri Lanka, 67-story tall Altea building. And this is a picture that was taken when the construction was underway. This is, so you can see the inclined tower out of steel was constructed without any support for 44 floors. So during the design, we actually checked the vertical tower for this for that particular condition, and you can see the center core is vertical, only the tower is inclined, so you can see it's a fairly stable building. Although the tower is inclined, the support structure or the main core or the spine of the structure is vertical, and here you can see the spine. And this is a huge building, larger building, and a huge heavy building, and now it's all out of concrete. So once these are corrected, this building was quite capable of providing adequate lateral stability. And this is a computer generated model because I did the checking, and then I also certified this building for the government of Sri Lanka as a safe building. And you can see it has special shape where this facade is not uniform. It's a fairly irregular facade, and this is the main wind direction as well. So the facade facing the main wind direction was very irregular, and it is by a world famous architect, and he designed some best buildings in Singapore as well and all over the world, and Moshe Shafdi. And there's another structural engineer who goes with him, is Predak Gera. He's from former Yugoslavia, and a very talented structural engineer who specializes in tall buildings and other buildings mainly. And I was the check engineer because we have to make sure that we certify. And coordinating engineers was Deepal Vikramasinghe and Mr. Bimal Fernando, one of my batchmates. So that's why I got a chance to get involved in this particular structure by creating the model and then analyzing it. And then the results of all this model was used by Mr. Bimal Fernando and his team to check all the individual members. So all that individual checking was done by them. All the modeling was done by me. And I also did some checking, and once we finished all the checking, we certified the building for building as safe to the government of Sri Lanka. Then there are so many other very fascinating buildings in Sri Lanka. This 46-story tall clear point, and again, you can see it's a living tree. And the specialty of this building is it's having 4.5-meter cantilevers, and these are all open architecture by architect Milroy Pereira. And so Marga Engineering is the owner and also the constructing company, and the structural design was by one of the best engineers in Sri Lanka, Mr. Nuwan Senaka, Engineer Nuwan Senaka. And today he has designed the tallest building in Sri Lanka, but still under construction. And it is Colombo 606. So Mr. Senaka has designed the tallest building having 77 floors in Sri Lanka. And he's a very good structural engineer. And he designed this building as well. There is Clear Point, sorry, Sky Garden. And then he also designed this Fairmount building. And Fairmount building is the first tallest building undertaken by Maga Engineering on their own, not for anybody else, for their own property development. Maga Engineering undertook this 32-story Fairmount building, and after that, immediately after that, they went for Clear Point, sorry, Sky Garden, and Sky Garden has double transfer floors, and again, Mr. Senaka designed these buildings. And then this is Prescott Monash. Again, I checked this building because this building was initially planned as an office building, but later converted to an apartment building. So because of that, they wanted to check it. So I made models, and this was checked in some 2007, year 2007. I checked this building. And so how do you get confidence when you are designing tall buildings? Can you get confidence by just following Euro codes or BSEN codes or developing a thorough understanding of fundamentals and theories? The most important thing is you must develop a thorough understanding. And because codes will help you, but they will never give you the confidence. Their codes will never give you the confidence to sign and certify a tall building, and especially very special shaped buildings like Altair. So if you want to certify, you must be thorough with your fundamentals, and that's why we always encourage our students to learn the fundamentals and then applications, rather than going directly into applications. And so I'll just take an example, and it's based about direct shear. Any continuous beam is subjected to loading. Uniform loading will have high shear at the supports. And when you are checking for shear, the BSEN or Euro codes allow you to check it at a distance d away from the face of the support, and then you can provide the same reinforcement up to the support. So if T10 is at 150 sufficient at a distance d away, you will provide the same reinforcement within the face of the support and the depth d. But if you look at earthquake behavior, plastic hinges always occur very close to the face of the support. So that means, you know, if you just satisfy the rule given in Eurocode 2, you may not have a very safe building. You must look at Eurocode 7 as well, where you will look at the earthquake behavior, and then take the precautions that are given in that as well. So basically, you have to have certain rules that have been developed by you. For example, if I am designing, I would not like to have a shear force more than 2 newtons per millimeter, because I know it's better to have a flexural failure than a shear failure. Flexural failure will always give us enough warning, whereas shear failure will give us less warning. So if I want to prevent a shear failure occurring, the ideal is, you know, I know the maximum shear may be about 4.5, but if I keep the shear stress at the maximum shear stress less than 2 newtons per millimeter squared, then the chances of shear failure is very remote. Then if I am getting a high shear, then I know the section I have selected is too small. That's why it's giving a shear failure. In a reinforced concrete structure, increasing the width of the beam by 50 millimeter or 100 millimeter will not carry a huge penalty. So it's worth increasing the width of the beam by 100 millimeter than having a very high shear stress. So you can have various rules, and the reason is you have to always think which failure you like to have. And then you have to ensure that particular failure occurs in the structure when it is overloaded. And then again, what you do is you will take additional precautions against whatever the failure that you like to have. And generally, I like the beams failing in flexure because it always gives sufficient warning. And always you have to think about the type of earthquakes that can occur. And Sri Lanka will not have earthquakes generally, but earthquakes are most unpredictable events. So if an earthquake ever occurs, it would be interplate type, because we cannot 100% rule out any earthquake in Sri Lanka. The reason is in 1614, on April 14th, there was a massive earthquake reaching a magnitude of 6 on Richter scale, about 15 kilometers away from the western coast of Sri Lanka. So the epicenter was only 15 kilometers away, and it caused massive damage to Colombo. So because of that reason, we cannot rule out, and also the deep studies undertaken by Dr. Kushan Vijayasundara and his team also have indicated that the western coast of Sri Lanka can face higher chance of earthquake than the eastern coast, although we often hear some tremors in eastern coast. So western coast of Sri Lanka can have a higher chance of earthquake. But again, what we have to keep in mind is intraplate type earthquakes, or the earthquakes that occur within a plate, is a very rare event. And even in an area where the plates are moving, earthquakes are not events that will occur every year. They are, again, they are not very frequent events. For example, if you look at Great Californian earthquake, which was of 1906, for the last 100 years or 110 years, we haven't had any major earthquake in that area except 1991 North Bridge earthquake. So everybody in that area or western coast of America now expects an earthquake can occur any moment. So what you have to do is don't blindly follow the codes. Always develop your own rules, and then you can use codes and do the calculations. And if the answers that you get do not tally with your rules, you can always recheck. But if you do not have your own rules, then there's no way you can check and ensure that your answers are correct. So let's see some guidelines. In buildings, if you are considering the vertical load carrying system, the main vertical load carrying system consists of columns, walls, pile caps, piles, and columns can be massive, but again, we can't increase the size of the columns too much. So because of that reason, we generally tend to use higher strength concretes in columns. And if you look at the Eurocodes, I will use only the cube strengths, because the Eurocodes allow us to use either cylinder strength or cube strength. So I'll talk only in terms of cylinder strength to avoid any confusion. We are allowed to go up to 105 newtons per millimeter squared or megapascal as the maximum strength. Whereas, in most of the constructions, you will find that we are using 25 or 30 megapascal concrete. And then walls can be of any thickness. And as in Altea, if you want, you can use diagrids. And the minimum reinforcement requirement in columns of and walls of walls according to Eurocode is 0.2%, VS code is 0.4%, but it's very usual to find that you are getting about 1.5 to 2.5% reinforcement. And when you are using a column of something like 1.2 meter by 1.2 meter, and when you are using some concrete like 100 megapascal, it's very usual to have massive column loads, like something like 80,000, 9,000 kilonewtons, or 80,000 or 90,000 or 90,000 kilonewtons or 9,000 tons. And you can just imagine the weight of a vehicle, a lorry, maybe about the container truck or a cement lorry carrying 600 bags of cement will have a total weight of only 40 tons. And here we are considering a column carrying a load of something like 80,000, 90,000 kilonewtons. So then if you are using 4 piles, each pile will have to carry about 25,000 kilonewtons. And to have a pile carrying 25,000 kilonewtons, we might have to go for 1.8 or 2 meter diameter. And when you go for such diameters, still, you might have to consider socketing into the rock 4 or 5 meters to ensure that adequate skin friction can be developed. And to sometimes to increase the skin friction, you might take very special precautions like breaking the rock around the pile, or having a groove, or with special tools or some special feature that will allow us to go for higher skin friction, like 1,000 or 1,500 newtons per millimeter squared. Whereas if you look at ICTAD specification, for normal conditions, it allows us to go only up to 200 kilonewtons per meter squared. Whereas now we are talking about 1,000 kilonewtons per meter squared or 1,500 kilonewtons per meter squared. That means we had to have very special precautions taken. Then only these very tall buildings can become practically feasible in our conditions. So our conditions are very favorable, but sometimes you have to do socketing great depth. For example, in Altea project, the rock was fractured. So to capture adequate skin friction, the piles were driven 10 meters into the fractured rock. And that gave massive skin friction. And when the piles were tested, even at 1.5 times the actual load, piles did not show any movement. So you can see, very special precautions are needed. And once you have this kind of knowledge, where you look at it in a more objective manner rather than just as a mathematician, it will give you a lot of confidence that your structures are good and correct. And you have to take adequate precautions when you are having columns, beams, piles, and especially the ground beams and so on. And so you can see, you can have very special shaped buildings. So if you look at a normal building, first I will talk about the normal buildings like 20, 30 story buildings that you will encounter often as apartment buildings. And one of the requirements is you will have a grid of 4.8 meter by 2.4 meter for car parking, that is the area. And then you will have multiple car parking areas, and then you might end up with a grid of 7.6 to 8 meters. And then the access to car parks also needs a minimum width of 7.3 meters. And because of all these things, you will find that you will be using one particular grid below the at the car parking level and another grid above the car parking. Now this is our usual concept. And here you can see the transfer plates. And transfer beams, transfer plates, and in this area, they had the swimming pool. In this area, they had the swimming pool, and the building turned twice in this particular one. And that is due to architectural requirements. And basically, tall buildings are cantilevers, so we have to have adequate precautions like concrete walls, concrete pours. And if the building is less than 10 floors, we can say all the lateral loads are taken by the shear walls. But when you have more floors, like more than 15 floors, you must consider the interaction between the frames and the shear walls. And then when the buildings become taller, we can employ outriggers, band beams, tubular structures, and bundle tubes. And in this particular talk, we'll be talking a little more about bundle tubes, because when you want to go for super tall buildings, bundle tubes will be the solution, because any other structure will not be able to provide adequate stiffness. And the tubular structure is an invention by a famous engineer called Khan from India, and these days we call the area that he was born Bangladesh. And he actually got the inspiration by looking at bamboos, and he thought, okay, bamboo is hollow in the middle, but it's very strong. Why it's strong is it's all the strength is confined to the outer periphery. So he thought, if you want to have tall buildings, then it should be like a bamboo. And people will use the inner part of the building, and the strength should be in the outer part. And if you want to have stronger bamboo, then you can combine few bamboos and make them stronger. So all his concepts are based on what he has seen as a kid in the form of bamboo. And then he actually converted all his tall buildings, like 100-story tall and 110-story tall buildings, into that particular form. And then in recent times, we have developed more forms. And one of those forms is called diagrids. And now we are familiar with diagrid because we are having a diagrid in our Altea building. So if you look at all these buildings, you can see rigid frame building, shear walls, belt trusses, frame tubes, tube-in-tube, truss tubes, bundle tubes, and truss tube without interior columns. So you can have different structures, and in the very tall Burj Khalifa, they have used some truss system. So tall buildings are very complicated structures. So because of that, we can perform manual analysis only to a limited extent. And if you want to get the real behavior, we have to go for mathematical models, and we can prepare mathematical models by using many software. And for example, all the students in our University of Moratuwa, they get a full license for Midas Gen, Midas Civil, and the whole Midas family of software. And we use SAP 2000 also to teach them, and they get limited exposure to ETABS, because when you know SAP, you can very easily learn ETABS. But we concentrate more on Midas family of software because they have the full license for Midas family of software, including Midas GTX and NFX and NFS and other modules. So when you are designing, you cannot blindly make mathematical models. You have to have some idea about the answers that you should get from mathematical models. Then only you can confidently use the mathematical models and the answers given by the mathematical models. So it's an art, and you have to actually master this particular art of getting, making a reasonable guess about the answers you should be getting. And for that, you need a thorough understanding of structural analysis and the behavior, the load transfers take place as well. So if you look at all these buildings now, you can see people are now thinking of 1 kilometer tall building. But if you look at all these very tall buildings, you can see there's no building at the top. It's only a spire. And not so tall buildings, you can see the top part of the building becomes very small. The habitable area in the top part of the building is small. And in all these buildings, you can see the top part is very small. No usable space. And another feature you can see is all these very tall buildings are having streamlined facades, glass facade, very expensive. Very, very expensive facades, because these facades should ensure that the facade is very strong. Then we also have to make sure the facade is out of material that is energy efficient, that does not allow too much solar energy coming in. Then there are so many requirements for these facades. So facades become extremely expensive. And because of that reason, most of our tall buildings are very expensive. They are much more expensive than 2-story or 3-story houses. So the reason is, for example, you can do a reasonable house today for about 10,000 rupees per square foot. But if you look at the apartment cost of most of the apartments in Colombo, they will say the apartment cost is about 18,000 to 24,000 rupees per square foot. That is not a good sign, because apartment buildings are very expensive, and that actually hinders people living in apartment buildings, tall apartment buildings, because tall apartment buildings, although you are not spending money for land, still the land also can be very expensive, like something like 15 to 25 million rupees per perch. So when you divide it by the number of floors, then you will get a lower value, but still the apartment cost is very high. So people find that, apartments are very expensive. They are not cheap. So, very often you will find the apartments can be 35, 40, 45, 50 million rupees. Whereas when you go suburban areas, you might be able to buy a land for about 20 million and construct a house for about 15 to 18 million. Still, you might find that you are spending less money than buying an apartment in Colombo. And some of the apartments in Colombo 7, in one of the prestigious projects, starts around 60 million. And some of the apartments in Altea, as I understand, starts about 70 million. And those are for the smallest apartments, and bigger apartments can be much more expensive. So this all indicates that, apartments, the tall buildings are very expensive. And it is a challenge for us to make them cheap. And today I'm going to show you how to make them very cheap and how to hit a cost comparable with a simple house, something like 6,000 to 7,000 rupees per square foot. And that would be an ideal solution to the problem where we are getting huge costs in apartment buildings. And if you can hit something like 6,000 to 7,000 rupees per square foot, then you can see we'll be in a position to provide apartments at a very affordable price, even to the middle income people. So that is our goal. So when you have tall buildings, when we make models, we have to have a good understanding of the behavior. So when you have a very tall building, the building can twist. And what are the repercussions of twisting of the building on individual elements like beams, columns, and so on? Can they be subject to torsional moments? The answer is no. Even if the building twists, individual members will not be subject to torsional moments. The reason is we know torsional moments have to be resisted by concrete and reinforcement, and reinforced concrete sections are not very good in resisting torsion. So as steel sections. So if you're having steel columns or concrete beams or steel beams, they are not very good in resisting twisting. And if you are going to have twisting, then we have to be careful. And then again, the main elements will bend only about one axis. They will not have biaxial bend. And columns will carry mainly axial loads. And when you have very large columns, the moments acting on the columns will not have much influence. And concrete walls will be very strong in carrying in-plane loads, but out of plane, they are not very strong. So if you are expecting some out of plane loads on walls, then better to go for thicknesses like 300 or 350 millimeters, so that the effect of out of plane movements will be very negligible. And slabs can carry flexure and they can provide in-plane stiffness, but slabs cannot make beams stronger. There's a misconception among new engineers that when they are modeling, they model the slab and the beam all together, and they think slabs can make beams stronger. It's a wrong perception. And you can get very wrong results by making such false assumptions. So that's why, you have to learn proper theories of finite element modeling, and also FEM programming when you are students, so that you will have a thorough understanding of the way that the FEM programs have been written, and that will give you a good understanding of how to do the modeling. And we call it art of modeling rather than science of modeling. And although these rules are there, there can be exceptions. So we must identify them early. And then there are so many other behaviors, because we have been talking about static behavior, but there are dynamic behaviors. So when it comes to designing, we have to see what a three-dimensional model can give us. A three-dimensional model can give us natural period of vibration of the building, and we can also get earthquake analysis and wind analysis results, good results from the 3D model. And then we can also get loads on columns, diagrids, and so on. And also if we are having transfer plates, then again we can get loads, bending moments, shear forces on transfer plates. But a 3D model will not tell us anything about the slab design, and 3D model or results cannot be used for beam design, because we are not getting pattern loading that the codes recommend us to consider when we are designing beams. So when you make a 3D model of a structure, you can see, you can have walls, transfer plates, pile caps, and when you are designing columns, you can have load reduction factors, and they are all allowed in both Euro codes as well as BS codes. But the time has come for us to stop using BS codes, but to move fully for Euro codes. And we hope very shortly CEDA will issue a directive saying that all building designs in Sri Lanka and any other structure design in Sri Lanka should be carried out according to Euro codes. And if you look at Road Development Authority, you will already see now Road Development Authority requires all their designs to be done according to Euro codes. So Road Development Authority has already moved, and we hope that CEDA will take correct action shortly, so that we will be forced to use Euro codes for all the structural designs, because we have not seen any advancement of British codes in the last 12 years. Since 2010, nothing has been done about British codes, which means, if you are using British codes, then you are using fairly outdated codes, and you must not be using British codes anymore. We must firmly move to Euro codes, because Euro codes allow us to have national annexures. And if you cannot have a national annexure immediately, we can always look for the national annexure of UK, because they are also having temperate climatic conditions and they are having warm summers. So because of that reason, most of the rules that they use in England can be applied in Sri Lankan conditions as well, because we are also having mild conditions. We are not having extreme desert conditions. So there's nothing wrong in using British standards or British national annexures of Eurocode in Sri Lankan conditions, but it's always good to have our own national annexure, so that we'll be able to have additional rules. And then when you are doing a model, here you can see a structure where below the in the car park levels we have beams and columns, and whereas above the car park levels we have apartments, and for apartments we have used walls. And then when you're in the car park level, you can analyze these structures, beams. And when you're analyzing a beam, one of the assumptions that we make is the beam is supported by a column and column does not settle. Now that type of assumptions would be pretty good for 2-story, 3-story, 4-story type buildings. But when it comes to tall buildings, you can have differential shortening of columns, and differential shortening means different adjacent columns can shorten by different amounts due to the variable axial forces acting on them. And if that is going to happen, we should not say, we are going to have a simplified model like this and we are going to have pattern loading. We must also look at it in a little more logical manner, because we are not including the wind loads in such a simplified analysis. And even if you have included the simple wind loads, still you'll find that the differential shortening should be given some consideration. So when you are designing, you will look at the bending moments, but you'll also consider the possibility that some plastic hinges forming close to the columns that can increase the span moment. So general tendency is, if I am doing designs, I generally tend to over design the beam section in the span, but I do not over design the beam section at the support. So the reason is all the codes allow certain degree of moment redistribution at the columns. So because of that reason, I do not really worry about the bending moment at the column, and also the effect of bending moment at the column due to the differential shortening. That also I will not worry too much. But to take account of all these unforeseen effects, I will over design the beam in the span section by about 10-15% or sometimes 20%. And then when it comes to the design of columns, you can always use the tributary area and calculate the loads on columns. And then beams also, you can have different sizes. So basically, it's possible to select beams, columns, and all the structural members in a tall building also by using simple calculations. But there's a big difference between a 2-story building and a 40-story building. In a 40-story building, we must, in addition to doing the calculation, we should take some assessment of risks. And risk assessment is a very good initiative. If you should train your mind to always be inquisitive and ask questions. This building is very different to a 2-story building. And I have designed 2-story buildings, but today I'm designing a 40-story building. What can go wrong in a 40-story building that you do not get in a 2-story building? That you have to always think about it. And then when you are designing tall buildings, again we have another challenge. Just because we have risk, we cannot be over designing. We have to be accurate with our designs. So how we optimize the building is we look at the structure elements that cannot go wrong. And we also look at the elements that things can go wrong. So if you take a normal building with beams, slabs, columns, slabs cannot go wrong. So we optimize the slabs. In beams, beams cannot go wrong at the support, but beams can go wrong in the span. So we over-design the span, but not the support. Then we also look at shear carefully, and also we also try and see whether torsion occurs. And then when it comes to slabs, we optimize as much as possible. But when it comes to columns, in the top part of the building, not a big problem, but in the bottom part of the building, we'll be very careful with the columns, because if anything goes wrong with a column in the bottom part of the structure, things can go wrong drastically. And we have seen one building collapsing in Miami, and nearly 100 people have died. So that type of collapses are totally unacceptable. And that collapse would have occurred due to the engineers underestimating the effects of construction sequence on the transfer plates. So I think that is the final finding of the teams. And so basically, when you are designing, you have to do a risk assessment, see which element can fail, and any element that you think has a tendency to fail, you will provide extra reinforcement and extra moment capacity and extra shear capacity. And if you think there's any element that can be subjected to axial shortening and induce plastic hinges, then rather than using very large diameter bars, you will use a number of small diameter bars so that the cracks will occur, but nobody will see the cracks. So likewise, you have to get a deep understanding of the behavior of the structure, and then do the detailing rather than blindly doing the detailing just by looking at the reinforcement area is 880. Then I can just provide 2 bars of 25 diameter, because each 25 diameter bar is 490 millimeters square. That type of calculations are not acceptable. You have to always see now what are the spacing, maximum spacing between bars, or whether it's better to have bars at a closer spacing than a larger spacing. If the area is 880, then you might see whether it's better to use 3 numbers of 20 millimeter bars than using 2 numbers of 25 millimeter bars. Not to say steel, but when you have 3 numbers of 25 millimeter bars, the crack widths will be smaller. So even if something goes wrong, still nobody will see any cracks, and no cracks means no investigation, nothing to worry. So likewise, you have to think about it. And when it comes to columns, always, you will see the possibility of columns failing due to providing too little reinforcement. And you will do a risk analysis, and then again see which level that you have to provide special additional reinforcement. And when it comes to concrete, also the same. And it's always good to use high strength concrete where necessary. But if you are using large sections like in a transfer plate, that means the structure is not optimized. So in such a situation, there's no need to go for high strength concrete for transfer plates, because the structure is not optimized. We are using a huge huge sections because the load transfer needs huge sections. And then when you are designing, again, you have to be very careful. And if you look at this particular column, you can see this is M33 and this is M22. Generally, we look at M33 all the time, but in this particular case, M22 is massive. So you have to always look at all the different moments, forces, every moment. You should not think, okay, I always look at M33 and I'm going to look at only that in the design. You must always look at all the different moments. And you can see when you are modeling in Sri Lankan conditions, it's always possible to model the structure, superstructure with substructure. And this kind of modeling is totally acceptable because we are having bedrock. We are having bedrock. So you can model the superstructure, substructure all together, and you can get accurate results. And also you might get situations where the transfer plates are there, And now you can see some of these walls are not on the beam, center of the beam. Some of these walls are on the side of the wall. And here you can see, again, you can see some of these walls are not on the beam, they are away from the beam. So which means some of these large beams can be subject to torsional moments. And if you look at some of these locations, beam locations, you will see that they are not on the center of the beam, the wall is on the side of the beam. That means the beam can be subject to torsional moments in addition to the bending moments. And to take account of that, you have to design the beams for torsion. And most of the time we don't design beams for torsion, but when it comes to transfer plates, you have to design transfer plates for moments. So you can get torsional moments, additional reinforcement, and sometimes you will find the shear links are not 10 millimeter now, they are of 25 millimeter diameter bars. The reason these shear links are not shear links, they are torsional links. So likewise, you have to develop good understanding of all different, because most of the time we have seen students concerned only to design for bending and shear, but you must also learn how to design for torsion, and you must use those. And then when you have massive sections, we have a different problem, and that we call delayed ettringite formation. That also should be paid attention. And to help you to sort this out, we have developed a set of curves that will help you to predict the maximum temperature that is reached by different types of concrete mixers. And you can download this particular paper just by typing MTR JAYASINGHE DE and DEF, delayed ettringite formation, and you can download this paper, read the paper. We have solved one of the biggest problems that all the engineers faced. Now these days, you can easily use this paper and predict the maximum go beyond 70, but 70 is given as the margin, and you can easily see how the concrete mixers you select will give maximum temperatures and whether they are over 70 or below 70. And then we talked about transfer plates, and we have so many buildings in Sri Lanka having transfer plates. This Keskat having a transfer plate here, and then we have to design them very carefully. And sometimes, they cannot be cast in one operation. You have to cast them into operations where first you design the first 400 or 450 millimeter thick slab, and to carry the weight of the concrete above, because it's very difficult to get formwork. And this is another example, classic example of having a transfer plate at 10th floor. This is Cinnamon Red Hotel. And when you enter at this level, then you have to go to 7th floor. And at the top of 7th floor, you get restaurant. And then above all that, you get a transfer plate at the 10th floor level. And to cast a transfer plate at 10th floor level, the biggest problem is the weight. And we solve that problem by going for a cellular raft, cellular transfer plate, where we cast the bottom part of the transfer plate first, and then we form the voids, and then we cast concrete around it. So that way we saved a huge amount of money. And I think the saving in that particular building from the original design had been about 200 million rupees. And that made it a profitable venture for Sankhya Lanka, the owner of the building. And then when it comes to piling, again, we have rules of thumb. For different pile diameters, we have different capacities. But these are for normal situations. But when it comes to super tall buildings or large buildings, that type of simple pile calculations are not applicable. You have to go deep into it, and you have to see how much socketing, extra socketing is needed to develop skill friction. And again, using the ICTAD guidelines is again too restrictive. You cannot rely on ICTAD guidelines. So what you do is you will go for pile load testing, PDA testing, and maintain load testing. And in a normal guideline for 1,200 millimeter pile is 6,500 kilonewtons. But in Altea, we used 11,000 kilonewtons for 1,200 piles, and 1,500 piles we use a normal guideline like 10,000 to 10,500 kilonewtons, but in Altea we use 17,000 kilonewtons. And when the structural engineer said, I want to use 17,000 kilonewtons for 1,500 millimeter pile, the geotechnical engineers did not like it very much, but we said, unless we can use 17,000, we cannot have such a tall building. Whether you like or not, we are going to do load testing and maintain load testing and PDA testing, and we are going to decide the pile load carrying capacity based on those testing rather than the predictions based on theories. And we found that our guess was better, that the maintain load testing and PDA testing proved that our guess of 70,000 is actually proper than using very low values. And then again, you have to think of piles in weak soil conditions, the lateral stability of piles, and for that again, we can use wrinkler swing methods, and we teach these methods for geotechnical engineers even in the final years of moratorium. Those who are taking large structures, they learn those theories, and for their comprehensive design projects, they use not only their own lecture note, they use even the MSc notes, because in comprehensive design projects we expect students to go deep into the subjects than finishing at very shallow levels. And you can see, you can have springs representing the soil conditions and so on. So a lot of information, a lot of things that you have to do that you do not generally do for a 5-story, 6-story building when it comes to tall buildings. But these are not super tall buildings. These are tall buildings, something like 20, 30, 40-story range. But when you move beyond 50 stories, now you are thinking of fairly tall buildings or super tall buildings. So super tall buildings, and this is the Twin Tower World Trade Center that collapsed due to the aircraft collision. And if I ask what is the area of each of these floors, then the answer is each floor had an area of 1 acre. Each floor had an area of 1 acre. And this is one of the tallest buildings, very efficient building, and it was originally called the Sears Tower, and then it was renamed Willis Tower. And this is a masterpiece by this particular engineer, and he was born in 1929. He died at the age of 53, but he is considered as a very good engineer. He is called Khan, Huslar Rahman Khan, who was born in North India, the eastern side, that we call Bangladesh today. But in 1929, they did not have a Bangladesh. It was part of India. So this is the building, very nice building, and it is out of tubes. So it is out of tubes, and we call it bundle tube concept. And Khan invented this bundle tube concept by looking at bamboos. And he looked at bundle bamboos, and he thought, okay, if I make the outer periphery of bamboos, the building strong, then I can have a strong building. So he use that. And then they added an observation deck, and that is called ledge. And you can actually go there and see about 1,500 feet below. And then this Burj Khalifa, again, they have used very special truss arrangement in addition to massive columns to stabilize the building, and stabilizing the building is always a problem when it is too tall. And although it's 860 meters tall, you will see that above 640 meters, there's no habitable space. And one of the problems with all these buildings is they are massive in the ground level, but they become smaller and smaller and smaller as they go up. That means you have massive area in the ground level, but the areas become smaller. That is not a very good thing, because you spend a lot of money and then but you don't get much space. So this Khan, he was born here in Bangla, in northern part of India. He was born here, and we have a special relationship to this part of India, and that is the King Vijay came from that part of India. So he's the language he spoke was Bengali, and 50% of the words of that language is out of Sanskrit, and most of those Sanskrit words are exactly the same as the Sanskrit words of formal Sinhala that we use here. And because Sinhala is a combination of the language, the Bengali language, and the language that the people in Sri Lanka spoke. So we have about, in our formal Sinhala, we have a lot of Sanskrit words, and those Sanskrit words are exactly same as the Sanskrit words that they use in Bengali language, which we have about 50% of the language is those original words. So one of the biggest problems with all these buildings is movement. And this is, the people who are actually looking, reporting about the traffic condition by staying in the 103rd story of this building, but they have a big problem. In a very windy day, the top of the building sways as much as 6 inches, the microphone sings back and forth, and people feel giddy, dizzy. So it is a problem. Then again, we look at another building. Everywhere in the world, they always use very smooth facades, and building movement is a massive problem. And in this particular building called Crown Resort in Australia, Sydney, Australia, which is designed by a Sri Lankan engineer. Sri Lankan engineer is designed by Dr. Dhammika Maharaji. He did BSc at Borotu in 1997, and he did PhD at Queensland University of Technology under the supervision of Professor Mahen Mahendran in 2003. He completed in 2003. Then he worked doing research, and then he worked under Mr. Nimal Perra, one of the greatest engineers in Australia, again a Sri Lankan. And then he became a master of the game, and then he designed the 120-story tallest building in Malaysia. And then he has designed this particular very complicated building in Sydney, Australia. And even today he is involved in two buildings. One is having 45 floors and another having 60 floors. And he is considered as the brain of the company of their Brisbane branch. It's a big company called Robert Bird Partners, owned by Singaporean government. And in this building, to stabilize the building, they use some tuned mass damper. And the cost of tuned mass damper was 40 million Australian dollars, and 40 million Australian dollars is about 6 billion rupees. So you can see, to make the buildings work, they spend a lot of money. And this tuned mass damper was designed by RWDI of Canada, and they also have a branch in India. And when we want to do all kinds of wind tunnel testing, we go to them. And RWDI is the wind tunnel testing company because it's set up by 4 greatest wind engineers of the world: Rowan, Williams, Davis, and Irving. So it is the company for wind tunnel testing. Australians go for that, and in Sri Lanka also we go for that. And 77-story twin tower by Mr. Nuwan Senaka, he used RWDI. And then Altea also tested by RWDI, and they do this kind of wind tunnel testing. And one of the features of all these buildings is they are having smooth facades and streamlined flow and vortex shedding problems. And then we are starting to see special buildings, and this is one of the special buildings in Sydney, located close to that particular tower. And if you look at this particular building also, it's a very special building because they are having not smooth facades, they are having very rough facades. So If you want to defy the wind, rough facade is the rule. And you can see it's rough. And the wind comes from this direction, it's rough. And when the wind comes in the other direction, it's okay because building is very stiff, no movement of the building. So Alta is a very stable building, although it's a very tall building and also inclined building, very special shape, but still it's a very stable building. So to overcome all these effects, we have to create turbulence. So we came up with a new model. And in our new model, what we have is, we are going to have a double facade. A double facade, I'll look at this particular building. We are going to have a facade here with handrails and then vertical columns at 2.4 meters, and then the handrail, the wall, parapet wall, the handrails, and then again we are going to fill that area with glass, laminated glass. You will ask why? The idea is, we want to have a facade so that no kid will have a chance of being blown away, and also we want to make sure that all these areas are protected, but we allow wind to leak. So when the wind is leaking, can wind exert forces? No. And in addition to that, we have columns like this, beams, facades. Why? We want to have lightning protection. When you have steel cage, we have a Faraday's cage. So the other idea is to create a Faraday's cage by having precast floating columns. And these are floating columns, and the floating columns, the walls, and again to create turbulence, we don't mount it at the front of the column, we mount the panel at the back of the wall, back of the column. So the idea is create as much roughness as possible, and with roughness you can prevent water shedding effect. And then we can have any kind of arrangement with a dual facade, and then you will find, because you are protected here, you can easily have a simple wall arrangement like large openings and so on, and you don't have any danger of being affected by wind. And then you'll ask why this type of arrangement has not been used, because this is a very good arrangement for tropical climatic conditions, but may not be a very good arrangement for cold climatic conditions. But on the other hand, you might think, okay, we can do various modifications and adopt the same thing for cold climatic conditions as well. And we have researchers already working on it, and Dr. Dhammika Maharaj is also working closely with us. And then, we'll not have straight balconies, we'll have twisting balconies. That means the projection of the balcony from the building will be a big value at one end, a small value at the other end. So building will look like twisted like this. And then Dr. Maharaj created the E-types model by using variable odd-shaped balconies. So all these are odd-shaped balconies rather than uniform-shaped balconies, and he created a 60-story building like this. And after creating all this 60-story building with scores at these levels, he said the load under each of these columns will be about 90,000 kilonewtons. So because of that, we have to expect something like 100,000 kilonewtons. And based on that, we proposed having 1.8 or 2 meter diameter piles under each column. And then you will ask, how about the spacing? These column spacings are about 9 meters, 10 meters. So there will be plenty of space for having four large diameter piles. And then again, you'll see, when you have such large diameter piles, it's not possible to maintain these basic rules like T times diameters. So generally, you have to go for something like 2 to 2.5 times diameters as the spacing between two massive piles. And so generally you will keep a distance of about 2 meters between two piles, because the diameter of the pile is 2 meters. So you'll see the basic rules that are followed by many engineers for small diameter piles are no longer applicable to large diameter piles. And if you ask an expert like Dr. Nalin, and he might say, keep a spacing of at least 1.5 meters to avoid one pile drilling, damaging the other pile. And so if you keep 2 times diameters with 2 meter piles, then again you'll see, by maintaining 2 times diameters as the spacing, you can still keep 2 meter spacing between 2 adjacent piles, and that would be sufficient to ensure the drilling of one pile not damaging the already completed other pile. Because we are using high strength concrete, the chances of such damage is also less, because we will be using very high quality cutting tools to create piles. So then, how about the partition materials in these walls, in these apartments? Do we have to use very expensive partition materials, or can we go for waste-based partition materials? So my idea is, no need to use very special ones, because already we are having a facade protecting the building, and then all the others are double facades, or the facade after a facade. So that means no need to have very strong materials, but you can use this kind of waste-based lightweight materials, but they are very strong materials. They are stronger than bricks and blocks, and you can see the load bearing, the way that these have been used for load bearing. And then we have tested them with proper load testing, and you can see they are very strong materials. And this particular house was constructed in 20 days. 2-story house completed in 20 days. So that's the advantage of all these new materials, and these materials are manufactured by the large factory of Mr. Niranjan Fernando, who is having huge wealth, because he has gone into the manufacturing based on waste materials. So there are many things that we can learn from all these. The main thing is, we have overcome one of the biggest problems of tall buildings. And here you can see this is the arrangement that you can easily use for 60-story building. Then how about 120-story building? What we do is we repeat this and create bundled tubes. Now this is one tube. Then what we do is we create additional tubes here, additional tubes around it. And by creating additional tubes, as they have done in Sears Tower, you get additional tubes, and similar to Sears Tower, you can see there are tubes. So create additional tubes. Then we can even think of going for something like with nine tubes like that, we might be able to go for massive heights like 1 kilometer tall buildings or 800-meter tall buildings. But the difference between our 800-meter tall building and the Burj Khalifa is, Burj Khalifa 800-meter height, it cannot be used, whereas our building can be used because it's not going to change its shape. It is the same shape, but the footprint can be about 2 acres. When you are thinking of something like 800-meter tall buildings, 8 acres, 2 acres or 3 acres, and in the lower part of the building, in these buildings, we no need to have the courtyard concept. We can have the complete building. So in the lower part of the building, all these can be the fully utilized floor, but as you go to the top part, you can have the center courtyard. And then this one tube, create more tubes, and then you can go for taller buildings. That is the concept. And then to do all these things, we have very good foundation material, and it is rock. And Sri Lanka is an ideal country for very tall buildings because we have the ideal foundation material. And if you try to do a foundation in any other country, you might spend about 3 times the foundation that you spend in Sri Lanka. If you are doing a foundation in Thailand, the cost, or Malaysia even, the cost can be 3 to 4 times the cost that you have to incur for the foundation that you do in Sri Lanka. So Sri Lanka has very favorable conditions, and then if you go for tall buildings with very cost-effective structures, we might be able to sell our apartments in tall buildings to many people, and especially those who migrated from our country might consider buying apartments for something like 100,000 Australian dollars or 80,000 Australian dollars, because to buy a house in Australia, they need at least 300,000 to 600,000 Australian dollars, depending on the location. And in some places, they need even 1 million Australian dollars. So buying a house, apartment for 100,000 Australian dollars in a building where there are a lot of shopping malls and all kinds of facilities will be very attractive for them. And we are in a position to create huge business in this way. And at a moment where Sri Lanka is facing dollar crisis, this might be one of the ways that we can come out of the mess. And the other way is organic farming, where if we can say all our food is certified as organic, we might be able to sell most of our produce to other countries at a premium price, and then again come out of the mess. So we have to think of all these things. And then not only that, sometimes we have to see, are these Euro codes sufficient? But again, you will see the Euro codes have certain limits, like the maximum cube strength is 105 megapascal. And sometimes when you go for super tall buildings, we might have to use concrete having 150 megapascal. And then you'll ask, can we make 150 megapascal concrete? The answer is yes, and we are now running research projects. And Mr. Nandana today indicated that there's a good possibility of sponsoring one of the students who is going to look at the 120 to 150 megapascal range. And we have one scientist, Mr. Ravi Nissanka, who is manufacturing all these very special admixtures in Sri Lanka. So with all these things, we are in a position to do many things in Sri Lanka. And also we are in a position to go for super tall buildings if the need arises. But and we have the support collaborations from Australia as well, with the top designers of Australia working very closely with us. So they will be doing the designs and we'll be checking. So which means any investor who is willing to go for tall buildings in Sri Lanka, they have a massive opportunity, because the local knowledge is available, materials are available, and alternative materials are available. So there are great opportunities for all the investors who are willing to invest in Sri Lanka, because there's a ready market with a huge population who have already migrated out of Sri Lanka, who are aging, and they might consider, rather than staying in a cold country that they are not very familiar, they would be much better off living in warm country like Sri Lanka in very comfortable apartments, and using their dollar pensions, converting to rupees, and using those rupees to live in Sri Lanka can again make it very attractive proposition to live in Sri Lanka in their retirement. And with that, we will be able to generate a lot of business in this country if we can improve the transportation system. And for that also, we are now in the process of working out the possibility of manufacturing trains in Sri Lanka, or making trains in Sri Lanka rather than importing. And our initial studies show we can make a train for 120 million rupees, whereas the imported one will cost 600 million rupees. So likewise, if we start doing things our way with our own resources in Sri Lanka, Sri Lanka has a great opportunity to come out of the current economic hardships created by various unplanned developments in the earlier days, and also COVID situation that prevailed in the last 2 weeks. So with that, I would like to conclude, and the message is, tall buildings are possible, and tall buildings offer many challenges, and then super tall buildings are also possible. But the difference between tall buildings and super tall buildings is in super tall buildings, we should not use transfer plates, whereas in tall buildings, we can use transfer plates. So that is the difference. So in super tall buildings, we have to make certain sacrifices in the lower floors because we are not supposed to use transfer plates. So we cannot optimize everything in a super tall building. Either the car park can be optimized or the apartment can be optimized. So we have to decide whether to optimize the apartment or the car park. But we should totally avoid transfer plates in super tall buildings. And also I have shown you how to minimize the wind effects, which means the super tall buildings can be designed for axial loads rather than lateral loads, which will make it very attractive to design super tall buildings in the range of 150 to 250 floor range, or going up to about 1 kilometer, especially in locations where we like to have so many people living with all kind of buildings with so many facilities like gymnasiums, walking tracks, supermarkets, food courts, everything in one building. And even you can have things like a school in the building, because in the low part of the building you don't need to have a courtyard concept, whereas in the top part of the building you can have the courtyard concept to provide adequate lighting for apartments. So with that, I wish to conclude. Thank you very much for your attention, and I hope you would have got some questions. And I would like to hand this over to Mr. Nandana after the acknowledgement. And I have to thank so many, and I have written so many names: Professor Chris Burgoyne, Professor Calladine, all the staff of Cambridge University, and my friends when I was a student, a PhD student at Cambridge, like Professor Alan Khan. All of them are now professors, and some are deans. And Professor Ahmad, Professor Tim Mayabel, who was our former external examiner, Professor Campbell Middleton, our current external examiner, Professor Alan Khan, who can be an external examiner for one of our engineering faculties. He's the deputy head Cardiff. Professor Simon Gust, head of department of Cambridge University, and so many at Cambridge University. And then the staff at Morato University, who helped us in so many ways, funded our research and so on. And then special thank for all the staff of Bath University who helped us to do a lot of research with Bath University, and also Professor Mahen Mahendran, who helped me when I was in Australia in 2003, and also again in 2018 for 2 months. So we have so many friends in Australia and also so many students in Australia. So we work very closely with them. Thank you very much for all the help that they have extended, and also Professor Priyan Mendis and his team. So thank you very much, Professor Priyan, as well. So then the question time, and I would like to hand this over to Mr. Nandana and his team, because I think they have some kind of panel discussion scheduled.
Thank you very much, Professor. I think no one in the audience is astonished or surprised by the fruitfulness and especially the innovative approach of your session, because we all know that the expertise that you have, and thank you very much for sharing your knowledge, experience, and exposure, well blended. Nandana is our General Manager, INSEE Concrete and Industrial Sales. Engineer Nandana Amrutudua, may I invite you to conduct the Q&A session of today's webinar session. Nandana, over to you.
Thank you, Dishan. Thank you very much, sir, for the detailed presentation you have done. We have quite a few number of questions. So
there are so many questions. Is that right?
Yes, sir.
Yeah.
Yes.
Shall I answer one by one?
Okay, sir. Please.
First one is Mr. Yoga. Yeah, Yoga. Sorry, I can't pronounce it. So is it possible to use shear link spacing proposed for tall buildings here for low rise? Actually, you can use this earthquake resistant detailing, and whether it's tall building or normal building, you can use the same guideline that is already given in the guideline prepared specially with the initiative of Mr. S.A. Karunaratna and Society of Structural Engineers. The second question is, Brian Eric, can you please elaborate the effects of modeling the slabs of finite element modeling? Basically, if you are modeling, when you are modeling, you can either model the slab, presence of the slab as a rigid diaphragm, or else, you can actually model it as a membrane, or else the slab. If you are modeling it as a slab, you have to reduce the stiffness to 30%. Whereas, if you are modeling the slab, you have to reduce the bending stiffness by 30%, up to 30%. Whereas, if you are modeling it as a membrane, no need, because ETAPS has the facility to model this as a membrane. But if you are using SAP 2000, then you can activate the rigid diaphragm option. Then next one is, sir, what is the impact of not considering more about column changes? Oh yes, column changes, due to different loads. That is actually, you cannot take this effect of axial shortening accurately. It was half calculations, half guesswork. So that's why I said, always when you are modeling, when you are providing the reinforcement in the beams, provide some extra capacity in the span, because if something goes wrong, then the bending moment in the span will increase, but because you have provided some extra reinforcement, the beam will not fail. Sir, what is the impact of the column? Yes, then sir, what are the construction stage analysis factors to be incorporated in the design? Actually, it depends on the aging factors, the way that the concrete strength changes. So the construction stage analysis is actually important only if the structure is consisting of a transfer plate. Otherwise, construction stage analysis is not very important. So basically, my rule is, if there's a transfer plate, due to the construction sequence, the dead load bending moments can increase by about 25 to 30%. So generally what I do is, because transfer plate is such an important key element, I simply increase the bending moment from the static analysis by 50%. And shear forces are increased only by 5 to 10%. I simply increase it by 25% and provide the reinforcement. The reason is, I will never take any risk with transfer plate, because transfer plate is a key element. So key elements must be over designed. And that is one of the reasons could be the reason for the collapse of that Miami building, because the designer has not over-designed, considered the construction sequence. And because of that, he has under-designed the transfer plate. When you under-design the transfer plate, the crack widths can be more. And when the crack widths are more and the building is very close to the sea coast, you can get corrosion. And due to the corrosion of reinforcement, there's a very high chance of building collapsing, like what we have seen in Miami. So, Chatur, the water structures, we are using 35A concrete, so the temperature graph will not change, because the temperature graph is based on the cement content. It is not based on the grade of concrete, it's based on the cement content, now the cementitious material content. And I strongly recommend you to go through the full paper, then you will understand how it has been written, analyzed. And all the details are given in the paper. And if you need further information, just send me an email. I'll clarify. Or we can have a Zoom meeting and we can clarify. So in case there's a software issue found piling doing testing, so basically you can do grouting. And these days, you don't do normal piling. You have additional. There are so many additional measures that you can take. And if you want to have learn about these things, I strongly recommend you to contact Dr. Nalini Silva. He is one of the experts who has done so much work with the Central Highway project. He has massive experience in all these different methods. So there are so many methods like sonic tubes and so many other techniques. And also now with access engineering, they are one of the researchers at Moratua. They are developing optical fiber-based technology as well. So there's a collaborative project going on with Access Engineering and Morato University. So there are so many things happening in the piling sector, so many advances. So I'm not the best person to tell everything. Dr. Nalin Disila is the expert. So I strongly recommend you to contact him. Is it possible for design super tall buildings that have human uniform flow areas? Yes, it's possible. With what I have shown you, now it's possible to have super tall buildings where the size of the building does not change, but we'll have a very strong building at the bottom of part of the building by not having the courtyard, but only the top part of the building. Because of lighting and other ventilation conditions, we can have the courtyard. But again, the courtyard also, because we are having PT slabs and complete rigid diaphragms, all those floors also will be strong. That's what Dr. Dhammika Maharachi told me. He said up to 60 stories building is super strong, and 70 stories also possible with the type of dimensions we considered. But if you are going more, we must go for bundle tubes. That means we must go for bigger footprint and bigger number of bundles, rather than using one bundle as the way that I have shown you. What I have shown is like one bamboo. Don't go with one bamboo, go with 4 bamboo or 9 bamboo. That's what he said. And Aravind, it's possible to design super right. Okay. Aravind, I have answered your one. Nimal Ranasinghe, Mr. Ranasinghe, what is the ground acceleration used in Hercule 1990 as Altea? Actually, we did not worry about earthquakes because we knew there is such a massive building, and the natural period of vibration of that building is 6 seconds. And an earthquake in Sri Lanka will last only 20 seconds, and before the building completes 3 cycles, earthquake will vanish. So earthquake, we knew there's no point in doing earthquake analysis for that building because that's a super strong building with the diagrid. So we do not bother to do that. What are the checks to be done for design of transfer floors and beams, and how to select appropriate depth and width for transfer beam? And so basically transfer beams are, if you are going with transfer beam is subjected to torsion. In torsion, the minimum dimension governs the torsional stress. So because of that, try and make them square. Try and make the beam square. So if the depth of the transfer plate is 1.5 meters, make the width of the beam also 1.5 meters. That is the rule. Is it negative check in pile caps, transfer beams? So pile caps are designed with strut and tie model. So when you design with strut and tie model, you don't have to do any crack width calculations. For the design of basement floor in high-rise buildings, is it okay to connect pile cap without the ground beam? With 200, no, actually using 250 to 300 maybe 300 may be okay, but not 250. But you have to provide double layers of reinforcement, and then you have to have pile cap. And if you think the lengths are too high, then you have better to provide ground beams. But if the pile caps are located close by, then you no need to provide ground beams. So that's all up to you. If you think something like 6-7 meters, then 300 meters is too small. Better to go with ground beams. Only in the middle part, but in the outer periphery, because you are having a peripheral wall, you might not need any additional ground beams. When we model with E-taps, beam moments are significantly differ from manual calculation. Yes, that is because you are using your modeling is not very accurate. So if you want to get the real, because unless you ideal way to model slabs is model it as a membrane rather than as a slab. Rather than using plane stress elements, you define it as a membrane. Then you can avoid most of these huge discrepancies. Sean, sir, let's say that we have column with grade 45 and the pile cap were designed for grade 30. You to consider any additional effect of column and pile cap junction. Yes, Actually, you have to be little careful because, the column size may be 1 meter by 1 meter, the pile may be 1.2 diameter. Then you will find that, although you have, then you can use a pile cap and ensure that the pile cap will do the stress distribution adequately. So although the pile is grade 30 concrete, the pile cap is will ensure that it's okay. But I would suggest that, using something like grade 35 concrete, if you are having 45, to keep the difference between concrete grades only about 10 newtons per meter squared. That in that situation, the impact will be very small. If you are using grade 45 for column, I would use grade 35 for pile rather than using 30. So you mentioned to reduce the slab thickness up to stiffness of 30%. Why do you need? Yeah, actually, I don't like this, modeling the slab band for reducing it by 30%. I would rather simply model it as a membrane, but that is actually given in the ETAFS manual. If you look at ETAFS manual, otherwise, basically slab is a member that is supported by the beam. So slab cannot strengthen the beam. But if you model the slab and the beam together without adjusting the stiffness, then you are saying slab is strengthening the beam. That is the wrong assumption. Well, the basic assumption is slabs are supported by beams, but slabs are not supposed to make the beam stronger. But if you simply model slabs and beams together, then you are saying slabs are stiffening the beam, which is a wrong assumption. Are there any differential effects of the structure due to rotational first mode of the oscillation? Any detrimental effect of that? Well, basically, it's better not to have first mode. The third mode should be the ideally torsional mode. You have to actually change the strong elements, and one way or the other make sure the dominant modes are the normal sway modes, not the torsional modes. So I have answered a lot of questions. So I think there's another section. Okay.
Okay, I think with the limited time, Nandana, are we concluding the Q&A session?
Yes, sir. So thank you very much for answering in your usual speed. So thanks again for answering most of the questions. So, due to some
I mean, you have requested Mr. Nandan and Dr. Kushan as well. Do you want to give them a chance to make any comment or anything?
Yes, sir, please, because now they are already joined us on this. So I would like if Mr. Nandana can note about this lecture.
Yeah. Thank you, Professor. Thank you, Nandana. I think we were listening to a complete design course summary, like he briefed the whole course within 1 hour. So we are very happy. I think most of our participants acquire a lot of knowledge about high-rise building. Also, I think if they were having any issue about the confidence of design plan, that was also solved by Professor's speech. I think now a lot of participants are very confident that we as Sri Lankan can do any high-rise building designs without.
Yes. Anything up to 1 kilometer or even more possible.
Yeah, that is important. Thank you.
Yeah, fully agreed, Mr. Nandana. Thank you for your kind words. Dr. Chandana, can you?
Dr. Kushan, do you have any comments?
Yeah, sure, sir. And thank you very much, Mr. Nandan, inviting me as a panelist, and thank you very much, and by the Professor Jayasinghe, so you have done a very wonderful speech, and that includes practical aspects, numerical aspects, design aspects. It's a blend of all of the key component to be familiar before you do design a high-rise building. And one of the important factor you may highlighted many times is to find the answer, you must know the answer. I think that is what the professor referred the confident you gain. Whatever
without that, you can never be confident.
Confident, exactly. You to find the answer, you must know the answer. I think in overall summary of the presentations, I would say that you must know the answer to find the answer. I think that is a key message passed to the younger generation by Professor with the great experience. And I would like to give one more message to the younger generations. Like even you develop such a complicated numerical model, as Professor very correctly said, you must know the fundamentals, right? You must feel the structure. What is the expected level of behavior? So what is the predicted behavior? And then you want to see that behavior in the numerical model, and then only you gain the confidence. That is what I said. You must know the answer to find the answer. Right, and I must thank Professor. I think you have done a very wonderful job, and I think that will be really helpful for the younger generations to build up their careers on seeing your personality. And thank you very much. Thank you very much.
Thank you,
Thank you, Dr. Vishan.
Thank you, Mr. Nandana.
Yes, Dr. Chandana, you want to add a few words about it?
Thank you very much, Mr. Nandana, giving me the opportunity. Sir, thank you very much for this very valuable lecture. Like I have gone back to my final year student days listening to you. And as Dr. Kushan correctly mentioned, you always are pushing us to touch the fundamentals, not to just dumbly like just adding values to the computer and then get the values. So that is very well highlighted here. And then I am really glad that you are being part of, and really proud to say that you are a member of our staff, sir. So thank you very much for this presentation, and please keep up all the good work. Thank you very much.
Thank you, Chandan.
Over to Dishan, over to you.
Okay, thank you very much, Nandana, General Manager of INSEE Concrete and Industrial Sales, for conducting the panel session. I think it is not a surprise, as I said earlier. Also, no one is astonished by the fruitfulness and the innovative approach of Professor Dishan Jayasinghe. And may I invite, before we conclude the session, may I invite Dr. Moza Balbaki, our Head of Products and Solutions Portfolio in Cement, to give away the vote of thanks. Dr. Moza Balbaki, over to you, sir.
Thank you, Dishan. First, really, I would like to thank everyone who attended to this wonderful session. Really, I would like to say that today we had more than 390 participants from the very beginning to the end. And on top of that, I would like really just directly go and thanks really from my deep heart, my gratitude. I don't know how to thank you, Dr. Jayasinghe, for your generosity, for the know-how, for all this really time you have spent to give us this wonderful, really wonderful presentation about what is relevant in tall building. And you make it very clearly what is difference between small building, tall building, and super tall building. What is really important. And also that very often we should go beyond standards. That is definitely very important, especially when we go for designing sometime out of the what I call the boundary, because the super tall building is designing out of the boundary. Therefore, we need to have some time a very good understanding of what a structure, how it could behave. This is really very interesting to see that. And even though I know from the material point of view, today, if you want to design a bridge for 50 years, the EN 206 is enough. Okay, but if you want to design a bridge for 100 years and plus, all service life modeling are requesting more, that we go beyond this normal standard. And that is very interesting to have heard that. Therefore, thank you so much. Thank you so much also to all the participants. It was really great to have you all again this session. As I said, more than 390 participants from the very beginning. I would like to also thank the panel, our friends, Dr. Chandana, Dr. Dishan, Dr. Kushan. Thank you so much, very much for also your intervention, you know. That was very, very great. Thank you for your generosity also. Therefore, of course, we would like really to, again, have this face-to-face, to be able to meet in person our guest speakers like Professor Dishan Jayasinghe this time, to have this relation, this personal contact, because it's very important, how we can bridge as human together. But of course, we are having some challenges, and I hope that we will go through these challenges very soon, that we can have again this knowledge sharing session, the I2I knowledge sharing session again here in Palyagoda, where I'm actually now sitting now and talking to you. And I hope soon we will be able to, to have this opportunity again to meet together and have some social activity just after this event. Therefore, we will continue every month, the last Thursday of every month, to have this, this webinar session. And we will do it with our expert, what I call the expert people in the industry, with academia, to bring topics that are relevant to you. And with that, I would like to finish and to say thank you again so much, and hope you are safe with your family. You have to stay strictly safe, of course, and see you next time. Thank you so much. Thank you so much.
Thank you, Dr. Moza Balbaki, Head of Product Solutions Portfolio in Cement. And thank you again, Professor Dishan Jayasinghe, delivering the super session on optimized and sustainable super tall buildings. Ladies and gentlemen, friends, let's catch up again with the 29th knowledge sharing session. Until that, be safe. Good night.
Thank you. Bye-bye. Bye-bye, everyone. Bye-bye, everyone.